is an engineering anomaly that rewrote subterranean physics. The Seikan Tunnel descends deep, cutting directly through the volatile sub-oceanic crust of Japan. To comprehend this immense engineering feat, we must analyze the crushing hydrostatic pressure profiles. At its lowest point, the structural alignment rests exactly 140 meters below the ocean. The structural path then dives an additional 100 meters beneath the unstable seabed sediment. At this extreme depth, the concrete lining must withstand a continuous load of 1.4 megapascals. That forces 14 kilograms of relentless water weight onto every single square centimeter of the vault. Imagine every linear meter of the arch resisting tens of thousands of tons of ocean weight daily. If a microscopic structural deviation occurs, the immense pressure transforms water into a supersonic hydraulic knife. This high-pressure stream can slice through heavy mechanical steel and solid rock in seconds. But the water pressure was only the first variable in this complex underground construction equation. The geological map beneath the Tsugaru Strait presents a chaotic matrix of sedimentary and volcanic rock. This specific geological formation is notoriously loose, heavily fractured, and constantly shifting under tectonic stress. To cross this nightmare, engineers designed specialized mechanical cutter heads instead of conventional models. Look at this early technical blueprint detailing the heavy, powerful boom header assembly machine. The rotating tungsten carbide teeth grind into unstable rock, generating intense friction and immense vibration. Behind the cutting edge, massive hydraulic pistons expand continuously to lock heavy steel rings into place. But drilling alone was suicidal, as high-pressure water channels threatened to breach the advancing face instantly. This dangerous condition forced the implementation of a critical solution known as high-pressure chemical grouting. Industrial pumps force a specialized mixture of cement slurry and liquid silicate into the bedrock. The injection pressure is carefully maintained at 2 megapascals, exceeding the natural resistance of the sea. Within minutes, this chemical compound hardens, creating an impermeable artificial shell around the tunnel alignment. This structural barrier seals microscopic cracks, preventing seawater from flooding the workspace during excavation. Simultaneously, massive logistics operations must manage the continuous removal of millions of cubic meters of rock. Heavy mechanical conveyor belts run 24 hours a day, pulling muddy debris away from the vault. Internal rail systems then transport the structural debris back toward the massive emergency shafts at Yoshioka. Every single mechanical component must operate in perfect synchronization within this cramped, moisture-slicked underground chamber. Any logistics delay at the muck removal station halts the entire advance, risking immediate rock collapse. As excavation advanced deeper, the operational logistics required continuous, complex environmental control systems. Heavy axial fans pump thousands of cubic meters of fresh air down through deep vertical ventilation shafts. This constant high-pressure airflow is critical to purge toxic accumulations of methane and hydrogen sulfide gas. Look at these industrial gas monitoring arrays, tracking subsurface atmospheric compositions every single second. The ambient temperature inside deeper geological strata rises rapidly due to geothermal gradients and mechanical friction. To mitigate this thermal stress, massive industrial chillers circulate freezing water along the structural steel framework. Engineers monitor these thermal readouts continuously, ensuring stability as ambient heat threatens to expand rock formations. Every single structural component must be evaluated against unexpected deformations caused by shifting tectonic forces. This brings us to the core structural shell design, where standard concrete mixtures are completely inadequate. Instead, the project utilizes a specialized high-strength shotcrete compound infused with dense steel microfibers. This advanced composite material is sprayed under intense pneumatic pressure directly onto the newly exposed vault. The steel fibers interlock within the matrix, instantly doubling tensile strength and preventing catastrophic rock bursts. Following the primary shotcrete layer, heavy-duty rock bolting rigs drive long steel anchors deep into bedrock. These mechanical anchors extend 5 meters into the geological formation, pinning loose blocks together like giant screws. This creates an integrated rock-concrete arch that allows the geological structure to support its own load. While the primary lining stabilized the perimeter, engineers faced the unprecedented challenge of active geological fault zones. The most dangerous segment was Fault Zone Number 2, heavily saturated with pressurized subterranean seawater. Every forward movement of the mechanical cutting head threatened to pierce the thin protective rock barrier. In 1976, during a routine exploratory drilling sequence, the structural integrity failed completely. A massive surge of seawater burst through the fractured bedrock, bypassing the primary chemical grouting barrier. The floodwater rushed into the pilot tunnel at an uncontrollable flow rate of 80 cubic meters per minute. Look at the high-capacity emergency drainage systems, instantly overwhelmed as rising water submerged electrical power blocks. The immense hydrostatic pressure threatened to destroy thousands of meters of completed lining through cascading failures. To counter this imminent catastrophe, site engineers initiated a tactical personnel evacuation while keeping pumps running. Heavy-duty steel bulkheads were mechanically sealed across the tunnel axis to isolate the flooding zone completely. For several agonizing days, the entire multi-billion-dollar project hung in the balance during pressure stabilization. Specialized high-output pumps were transported down vertical access shafts to increase total drainage capacity significantly. These industrial units slowly lowered the water level, allowing engineering teams to inspect the damaged face safely. The investigation revealed that the high-velocity water jet had carved out a massive cavity behind the arch. To repair this structural void, workers developed an advanced, multi-stage concrete backfilling sequence under extreme constraints. With the catastrophic water inflow fully contained, the engineering team pivoted back toward the main structural alignment. This required transitioning from early blast and drill methods to utilizing advanced tunnel boring shields with larger diameters. The mechanical shield structure features a reinforced circular steel shell designed to support unstable rock directly. Look at these hydraulic thrust cylinders, generating thousands of kilonewtons of continuous force to push forward. As the massive cutting head rotates, specialized alloy discs shear away thin layers of volcanic rock. The pulverized debris is mechanically gathered into an internal hopper, preventing accumulation at the active face. Directly behind the advancing shield, a heavy mechanical erector arm lifts prefabricated concrete segments into position. 6 individual concrete segments are locked together sequentially to form a single completed structural ring. Each structural ring is engineered with integrated elastomeric gaskets to seal joints against high-pressure seawater. The operational tolerance for positioning these heavy concrete components is strictly maintained beneath 2 millimeters. Any spatial alignment error beyond this technical limit would introduce severe stress concentration under ocean loads. To ensure absolute precision, engineers apply an automated laser guidance matrix that cross-references positional data three-dimensionally. This laser tracking unit calculates the coordinate vectors of the shield relative to exact geodetic markers. The spatial calculations are processed instantly by the mainframe, transmitting real-time steering corrections to hydraulic valves. This closed-loop automated guidance system allowed the heavy assembly to advance continuously through complex fault matrices. As the tunnel boring shields advanced steadily from both sides, operational focus shifted to alignment. Engineers on Honshu and Hokkaido coordinated coordinates continuously, tracking the spatial progression of dual excavation faces. The technical challenge was maintaining three-dimensional spatial accuracy across 23 kilometers of dark, isolated bedrock. Look at these gyroscopic survey units, measuring Earth rotation vectors to stabilize coordinate trajectories under the basin. Any spatial alignment error accumulating over the long distance would cause separate tunnel paths to miss completely. To eliminate this risk, secondary verification teams cross-referenced laser guidance data using deep vertical coastal boreholes. The geodetic data confirmed that internal guidance systems were operating within an optimal technical tolerance profile. Simultaneously, mechanical stress testing on completed structural rings continued to ensure stability against fluctuating tidal loads. Ultrasonic transducers were mounted along concrete vault walls, measuring sound wave velocity to detect material microcracks. These non-destructive testing procedures confirmed that the reinforced steel fiber shotcrete matrix held loads with absolute efficiency. This brings us closer to the historical engineering climax, where the final rock barrier remained. The remaining rock wall between the Honshu and Hokkaido pilot tunnels was reduced to 12 meters. Workers carefully drilled small explosive placement cavities across the entire rock surface under high supervision. Detonation lines were connected to a central electronic firing panel located in a reinforced safety chamber. The technical team initiated the final blast sequence, sending controlled electrical current to ignite the charges. The controlled explosion shattered the remaining bedrock barrier, clearing smoke and revealing the unified sub-oceanic path. Engineering crews from Honshu and Hokkaido moved forward across rocky debris, marking the historic breakthrough. Look at the final trilateral geodetic readings, confirming the spatial deviation between shafts was under 20 millimeters. This microscopic tolerance profile across 23 kilometers represents an absolute triumph for Japanese precision mechanical guidance. With the pilot tunnel breakthrough finalized, work accelerated to expand the main vault to its final diameter. Heavy-duty steel forming rigs were positioned inside the excavated space, preparing for the final concrete pour. Massive concrete transit cars moved continuously through the shafts, delivering thousands of tons of waterproof material. Mechanical pumps forced the dense concrete matrix behind steel forms, creating a smooth lining 70 centimeters thick. This permanent structural shell provides the secondary defense layer, isolating inner infrastructure from the corrosive environment. Following completion of the concrete shell, logistics teams initiated the complex installation of the dual-gauge railway. Heavy maintenance trains transported long welded rail segments down the grade, laying them onto concrete beds. These continuous welded rails eliminate joint gaps completely, preventing mechanical vibration stress as heavy trains traverse. Automated rail fastening machines secured the steel tracks, torque tightening each heavy bolt to exact engineering specifications. Simultaneously, electrical engineering teams began stringing high-voltage overhead catenary lines to supply power to train sets. Substations built inside massive rock chambers were energized, stepping down grid voltage to 25 kilovolts AC. With power systems successfully energized, engineers initiated integration testing of the tunnel's massive climate control network. Giant dampening louvers installed inside ventilation caverns adjust their angles mechanically to regulate intense aerodynamic forces. This heavy-duty ventilation infrastructure prevents dangerous atmospheric pressure waves from building up as high-speed trains pass. Look at these secondary drainage channels, cutting deep along the track base to funnel seepage toward sumps. Even with an impermeable concrete lining, the sheer hydrostatic load forces minor moisture filtration over time. This residual water drains continuously into the main emergency pumping stations situated at the lowest alignment points. Massive high-output multi-stage centrifugal pumps operate on automated float switches, maintaining dry track conditions constantly. These heavy industrial pump arrays expel up to 100 tons of filtered water per minute. Simultaneously, structural maintenance crews install long arrays of fiber optic strain sensors along the inner vault circumference. These optical cables utilize light refraction changes to measure structural deformation down to a fraction of a millimeter. The automated diagnostic matrix transmits structural telemetry directly to the central control center on the Honshu mainland. Technicians monitor these real-time structural load profiles, ensuring tectonic shifts along fault lines do not compromise safety. Following the instrumentation phase, final clearing operations commence to prepare the double-track line for actual testing. Heavy mechanical ballast regulators swept the line, locking the stone foundation secure around concrete track ties. The overhead clearance profiles were verified using automated laser scanning cars, confirming complete absence of any obstruction. With all structural clearance profiles fully validated by laser scanning, the project entered high-speed rolling stock testing. A specialized multi-car Shinkansen test train set was positioned at the Honshu terminal portal, lifting its electrical pantographs. The main traction substation stabilized transmission lines, ensuring constant alternating current flowed through overhead copper wires. The test train accelerated smoothly down the grade, leaving sunlight and entering the concrete portal undersea. Look at these telemetry monitors inside the train's diagnostic cabin, tracking axle vibration vectors and contact forces. Aerodynamic monitoring arrays measured severe air resistance spikes as the train compressed air columns inside the tunnel. Massive air shafts and mechanical dampening louvers operated flawlessly, dissipating high-pressure wavefronts before causing instability. The train crossed the deep subterranean geodetic boundary line, entering the segment 140 meters below. Fiber optic telemetry arrays running along the circumference confirmed that concrete deformation variations remained at absolute zero. The high-speed train reached its designed cruising velocity of 260 kilometers per hour inside. The solid concrete track beds absorbed the immense dynamic kinetic load, providing perfect guidance for steel wheels. The test vehicle transitioned smoothly past the deep emergency evacuation stations at Yoshioka, flashing past safety markers. The successful completion of the high-speed transit test proved the structural integrity of the Seikan Tunnel. This massive megaproject stands as an absolute monument to engineering precision, connecting islands through high-grade infrastructure. The completed line permanently integrates regional economies, bypassing unpredictable maritime weather risks through sub-oceanic logistics. Every single mechanical subsystem, from high-output pumps to automated ventilation networks, operates continuously to preserve this marvel. Humanity has successfully bypassed physical barriers of the ocean crust, establishing a permanent artery through volatile bedrock.
This new underground hub is a triumph of modern engineering, designed to handle the increased capacity for the next century. The scale is truly unprecedented. Standing here on the new high-speed platform, the sheer scale of the engineering is apparent. This train represents the future of British infrastructure.
This documentary is for education only. Based on real sources, theories are not facts.